Hi everybody! So today's video is going to be about task 2.1, which is the beginning of our second chapter for Math 1. In this task, we have 4 learning targets. The first one is I can graph a linear function given an equation, a table, or a situation in context. The second learning target is I can graph an exponential function given an equation, a table, or a situation in context. And the third learning target is I can identify if a relationship is discrete or continuous and support my reasoning. And last but not least, I can identify if a relationship is linear or exponential and support my reasoning. So I want to take a second and just point out some of the key ideas we're going to be doing today. We are going to start talking about linear functions, and we're going to be making graphs of linear functions. We are also going to start talking about graphing exponential functions and kind of what is an exponential function and how do you graph it. We are also going to talk about identifying if a relationship is discrete or continuous. So those are some of the new vocabulary words for this unit, discrete or continuous. And last but not least, we are going to talk about how do you determine if a relationship is linear or exponential. So what is the difference between linear or exponential and how can you tell? Let's start with some vocab. So the big new vocabulary words for this unit are the words linear and exponential. Let's talk about linear functions first. A linear function is a sequence. A function is linear if the sequence is arithmetic with a common difference. So what I want you to do is think about linear as being a new name for an arithmetic sequence. Sometimes instead of calling it arithmetic, we call it linear. Now this makes sense because the word linear actually has the word line built in. And we know that a function is linear because the graph looks like a straight line. Now that's the same thing we already knew about arithmetic sequences, is that it's arithmetic if it looks like a straight line, and now we're going to also say another name for that is linear. Now we can also write equations. An example of a recursive equation for a linear sequence would be something like this. F of x is equal to f of x minus 1 plus 3. And the reason that we would know, and let's give it a starting term. Hold on. F of 1 is equal to 7. I'm just making this up. The reason that we would know that this is a linear sequence is because we can see here at the end that the pattern is adding 3 each time. So the common difference is equal to 3. It's also an arithmetic sequence, which means now we're going to call that linear. So arithmetic and linear are kind of the same thing. An explicit example would look like this. F of x is equal to 3x plus 2. Or you might see the problem written as f of x is equal to 2 plus 3x. So you can see it with the starting term at the beginning or the starting term at the end. Either way, it's going to be arithmetic, which makes it linear. Now, the second type of sequence we're going to really focus on in this unit is exponential. So exponential is another name for a sequence that is geometric. So anytime you have a geometric sequence, we're going to call that exponential. Now that means it's also going to have a common ratio. So instead of a common difference, these are sequences with a common ratio. Now that means that a function is going to be exponential if the graph looks like a curved graph. A recursive example would be f of x is equal to f of x minus 1 times 2, where the starting term might be 7. And the reason that we would know that this is an exponential function is because this times 2 means that the common ratio is equal to 2, and it also tells me that this is a geometric sequence, which means we would call it exponential. Now, an explicit example would be f of x is equal to 3 times 2 to the x power. And when we say exponential, the reason we call it that is because this equation has an exponent in it. Now, that's kind of where the names came from. The name linear came from the fact that the graph looks like a straight line, and the name exponential came from the fact that the equation has an exponent. All right, that is some basic vocabulary, and we're going to be using those vocabulary words in the next few problems as we look at some graphs, some tables, and some sequences to kind of explain our thinking and use some vocabulary to describe them. So scenario number 1 here says, my little sister Savannah has a piggy bank. She started with 5 pennies, and each day when I come home from school, I give her 3 more pennies. Now, when I read this story, there are 2 important pieces of information that jump out at me. She started with 5 pennies, and each day I give her 3 more pennies. So started with 5 pennies means that in the table, the beginning value is going to be 5. She starts with 5 pennies. And each day when she comes home, I give her 3 more. So to get to the next number, I would add 3, which gives me 8. I could add 3 again to get the next number, which is 11. If I add 3 again, I get 14. And if I add 3 again, I would get 17. So that's kind of how I could fill in that table using the story in the problem. Now, if I wanted to make a graph of this scenario, I need to start with some labels. So the inputs on this graph are days, which means the bottom here would be days. And the outputs on this graph are pennies, which means the label on the y-axis would be pennies. And if I were to graph these points, I would make a graph and it would look like this: 0, 5, 1, 8, 2, 11, 3, 14, 4, 17. Now, this should be kind of a nice review of something that we've done before. This should feel very much like problems that we did in Module 1. And if I were to ask you to describe the sequence, you would say that this is an arithmetic sequence. And there are a couple different reasons that you could use to describe that. You could say because the pattern is adding 3 each time. You could say because the graph has a straight line. Both of those are good options. Now, in this unit, we're going to also ask you, is this linear or exponential? The thing is that as soon as you say arithmetic, you can automatically say linear because every arithmetic sequence is linear. To support your reasoning, you would say, since the sequence is arithmetic, the function is linear. You could also say because the graph makes a straight line. And you could also say because the pattern is adding 3 each time. Now, you do not need to say all 3 of these reasons. I just wanted to kind of show you that you do have some options here, and there are 3 different ways to explain your reasoning. For the next problem, it says, at the beginning of the summer, I decided to fill my pool. The pool started with 5 gallons of water, and the hose was filling the pool at a rate of 2 gallons every minute. Now, in this story, it says the pool started with 5 gallons of water, and the hose was filling the pool at a rate of 2 gallons every minute. So just like before, the 5 gallons of water is going to be my starting value. And since I'm adding 2 gallons every minute, I would use that pattern to fill in the rest of the table. So I would get 7, 9, 11, and 13. Oops, plus 2 which makes 13. Once again, I want to label my axes. In this case, it would be minutes and gallons. And I want a graph here. So 0, 5, 1, 7, 2, 9, 3, 11, and 4, 13. But now this problem, I'm going to ask you to think about something a little bit new. Up until now this year, we've never connected the dots on our graph. And the reason we never connected the dots is that you're never going to have half of a penny. You're never going to end up with, 5.5 pennies. And there's never going to be like a time that you get pennies in the middle of the day. So these dots should not be connected because it's not something that you would kind of continuously change. It's not going to go from 5 to 5.1 to 5.2 to 5.3 all the way up to 8. It just jumps straight from 5 to 8. However, when you're filling water in a pool, that water flows in gradually. So, because of that, you're not going to just jump straight from 5 to 7 gallons. You're going to gradually increase your amount all the way up to 7. Because in this scenario, it's water that's flowing, it actually does make sense to connect the dots here. So, in this case, I would connect the dots on this graph and I would put an arrow on the end because I'm going to keep adding more water. Now, when we describe this sequence, we would still call it arithmetic, and we would automatically say that that also makes it linear. And our reason, I like to use the reason because the graph makes a straight line. Which I can say because I made the graph here. But the big new thing that I want you to realize about this problem is that this time we connect the dots because water flows gradually. So one of the new things in this unit is that we're going to need to make a decision about whether to connect the dots or not, in addition to whether the sequence is linear or exponential. Let's look at another scenario. So the next scenario would be my sister started with 5 pennies in her piggy bank. So just like before, she starts with 5, but each day the number of pennies she has doubles. So in this case, there are 2 important pieces of information here. She has 5 pennies in her piggy bank. Each day the number she has doubles. So we're going to start with 5, and doubles means multiply by 2, which means I get 10. If I multiply by 2 again, I get 20. If I multiply by 2 again, I get 40. And if I multiply by 2 again, I get 80. I'm going to add some labels to my graph. So I have days here, and I have pennies here. And I'm going to sketch my graph. So 0, 5, 1, 10, 2, 20, 3, 40, and 4, 80 would be like way up there. I'm not going to worry about that because it's not on the graph. It's not going to fit. Now this to me is a multiplying pattern and it's a curved graph. So we're going to say that this is geometric. As soon as you say geometric, you're going to automatically say exponential. And our reasoning would be because a geometric sequence is an exponential function. You could also say because the pattern is multiplying by 2 each time. And you could also say because the graph is curved. Now, just like before, you don't need to say all 3 of these reasons. I just want to give you some options. The next scenario says, at the end of the summer, I decided to drain my 50-gallon kiddie pool. I noticed that after each minute, there was only half as much water left in the pool. So we've got a 50-gallon kiddie pool. Each minute, there's only half as much water left in the pool. So we're going to start with 50 gallons. And to fill in the rest of our table, we're going to multiply by 1/2, which means I get 25. If I multiply by 1/2 again, I get 12.5. If I multiply by 1/2 again, I get 6.25. And if I multiply by 1/2 again, I get 3.125. To make my graph, I'm going to label. So the bottom would be labeled minutes because that's the input, and the side would be labeled gallons because that's the output. When I graph this, I would do 0, 50, which is right up here, 1, 25, 2, 12.5, so like halfway in between the 10 and the 15, 3, 6.25, a little bit above the 5, and then 4 would be 3.125, so right down here. Once again, based on the pattern and the graph, I would say that this is a geometric sequence, which means I would automatically choose exponential. And to support my reasoning, I would say because the graph is curved. Or if I didn't have a graph, I might say because the pattern is multiplying by 1/2 each time. But just like before, we need to make the decision about whether to connect the dots or not. Now, in this first scenario where we're counting the number of pennies, I'm not going to connect the dots. And the reason I'm not is because I'm never going to have like 5.5 pennies. I'm never going to jump and kind of cut pennies in half. However, in this second graph, if it's water flowing out of a pool, it's not going to jump straight from having 50 to 25 gallons. It's going to gradually go down. So I would connect the dots with a nice curved graph here that kind of flattens out at the end. You can see from the shape of the graph, it's kind of flattening out over here on the side. And this time we do connect the dots because water flows gradually. Now, this idea of whether we should connect the dots or not is the second big idea of this unit. So the first big idea is just linear is the same thing as arithmetic, exponential is the same thing as geometric. But the second big idea is the idea of a discrete or a continuous relationship. So these are the two big new vocabulary words that we're going to focus on now. Discrete versus continuous. A discrete graph is a graph that uses points that are not connected. A relationship is going to be discrete if it's something that you can count, like pennies in a bank. I wouldn't ever measure pennies. I wouldn't say, like, take out a measuring stick to figure out how many pennies there are. I would just say, here's how many pennies I could count them 1, 2, 3, 4, 5. Now, a continuous relationship is a graph that uses points that are connected. So now we have a choice. Do we connect or do we not connect? A relationship is going to be continuous, so we are going to connect the dots if it's something that you can measure. So for example, if you would measure it using a ruler or a measuring cup, that's going to be something where you do want to connect the dots because it goes gradually. An example would be the amount of water being drained from a pool because water flows gradually. An example, a question of what you might see is this. The average bamboo plant grows 3 to 5 feet every year. Would that relationship be continuous or discrete? So let's think about growing. If I was measuring the height of a bamboo plant, this is something that I would measure with a ruler or a yardstick or something. So because it's something that I measure, I don't count how tall a bamboo plant is, I measure how tall a bamboo plant is, I'm going to say that this is a continuous relationship. The bamboo plant is not going to jump straight from 3 to 5 feet. It's going to gradually grow. So I'm going to measure it with a ruler. If I wanted to explain my reasoning, I would say that the bamboo plant is something you would measure. Now, if I was talking about pennies in a bank, I would say discrete because that's something that I would count. All right, that's it for today. Thank you guys so much for watching. I hope you have a great day, and I will see you for some practice.